The year is 2026, and the digital world pulses with an insatiable hunger. AI models, once confined to research labs, now orchestrate supply chains, compose symphonies, and predict scientific breakthroughs. They are not merely growing. They are exploding in complexity and scale, demanding ever more power, more processing. But beneath this dazzling progress, a silent crisis has been brewing, a fundamental bottleneck threatening to starve the very engines of innovation. The problem isn't necessarily the speed of our processors. It's how quickly they can feed their voracious appetites. Imagine a brilliant chef, capable of preparing a five-star meal in seconds, but forced to work in a kitchen where ingredients arrive one tiny spoonful at a time. This is the reality for today's advanced AI. Our graphics processing units, or GPUs, are supercomputers, capable of trillions of operations per second. Yet, their potential is often wasted, sitting idle, waiting for the immense datasets needed for training or inference to arrive from memory. Existing high-bandwidth memory, while powerful, is increasingly inadequate, often over-provisioned in some aspects like write capacity, while severely under-provisioned in the read bandwidth and sheer density that modern AI demands. It's a fundamental architectural limitation, a memory wall, that keeps our most ambitious AI aspirations firmly grounded. But just as the challenge became most acute, a solution began to crystallize. Enter High Bandwidth Memory 4, or HBM4. While its predecessors laid the groundwork, HBM4 is poised to fundamentally redefine this landscape by 2026. Think of it not as building a wider road, but as constructing a multi-story, vertical data skyscraper directly next to the processing unit. Instead of data traveling across a vast, sprawling factory floor, it moves vertically, instantly, between floors. This architectural revolution, stacking memory dies atop each other and connecting them with incredibly short, dense pathways, shatters the traditional memory wall. HBM4's genius lies in two core advancements: vastly increased bandwidth and unprecedented density. It achieves this through more memory channels, significantly higher data rates per pin, and the ability to stack even more individual DRAM dies within a single package. We're talking about bandwidths that can exceed 1.5 terabytes per second, sometimes even 2 terabytes per second, per stack. This isn't a marginal improvement. It's a generational leap. For AI, this means models can access colossal amounts of data almost instantly. Training cycles that once took weeks can now be slashed to days, while real-time inference for complex applications becomes genuinely achievable, opening doors to previously impossible AI capabilities on the bleeding-edge B300 generation of hardware and beyond. But here's where everyone is wrong about HBM4. It's not simply about making memory faster. A superhighway is useless if the traffic management system is chaotic. The real magic happens when HBM4's raw power is paired with intelligent system-level design and sophisticated software. Features like unified memory, advanced caching algorithms, and asynchronous prefetching become even more critical. These aren't just technical details. They are the unseen orchestrators that ensure HBM4's incredible bandwidth isn't wasted. They prevent bottlenecks from shifting further down the line, ensuring that the right data is available at the right time, maximizing every single byte of HBM4's potential. Without this intelligent integration, HBM4 would be a Ferrari stuck in traffic. With the memory wall crumbling, the true potential of next-generation AI is finally being unleashed. Imagine conversational AI models so large, so nuanced, they can instantly grasp context across hours of interaction. Think of autonomous systems that can process a torrent of sensor data in milliseconds, making split-second, life-critical decisions with greater accuracy. In healthcare, HBM4 accelerates the analysis of vast genomic data for personalized medicine. In scientific research, it powers simulations of unprecedented scale and fidelity, compressing years of computation into months. HBM4 isn't just making AI faster. It's making new kinds of AI possible, fundamentally altering what we once thought was beyond reach. Yet, HBM4 is not a panacea. This groundbreaking technology comes with its own set of challenges and trade-offs. The sheer complexity of stacking so many dies, connecting them with thousands of precise through-silicon vias, and integrating them directly onto a processor interposer means higher manufacturing costs and intricate thermal management requirements. Cooling these dense stacks of memory efficiently is an engineering feat in itself. While HBM4 dominates for raw bandwidth, other innovative memory architectures, like the proposed managed retention memory, are also being explored. These might offer different compromises between density, latency, and cost, hinting that the future of memory for AI is not a single, monolithic solution, but a diverse ecosystem, each optimized for specific workloads and constraints. HBM4 stands as a critical evolutionary step, a testament to relentless engineering to overcome fundamental physics. It's shattering the memory wall that constrained AI's ambitions, paving the way for models that are larger, smarter, and more integrated into our world than ever before. But the quest for speed and efficiency is unending. As AI continues its exponential climb, even HBM4 will eventually find its limits. The next frontiers will involve even more radical approaches, perhaps optical interconnects, or entirely new paradigms like in-memory computing where processing happens directly within the memory itself. For now, in 2026, HBM4 is the key, the quiet powerhouse unlocking AI's extraordinary future, proving that often, the biggest breakthroughs happen not in the spotlight of processing power, but in the unseen, intricate dance of memory.